I'm going to talk about ProAZ today, and in particular predicting fractures with ProAZ. And our goal in doing this is to remotely detect informations about the fractures in the stress field in order to help with the development of unconventional and tight hydrocarbon reservoirs. And the key thing about this is that fractures and stress cause the Earth to become anisotropic, which is seismically observable. And then by observing the P-wave azimuthal amplitude and travel time variations, it's possible to infer information about the fractures and their orientation. And our goal is to create a display that looks something like this, where we have both magnitude and orientation information, and we try and relate the magnitude information to things like fracture intensity or to the anisotropy. And our focus is P-wave azimuthal seismic data. There's certainly other types of information. There's converted waves, there's shear waves, but most people have P-wave information quite readily available. And there's two main things that we're going to try and focus on. One is azimuthal travel time variations. Here we're looking at a constant offset, and then the azimuth is varying within these yellow-gray panels. So we're looking at travel time variations, or alternatively looking at amplitude variations. And then from that, we're going to try and infer something about the anisotropy within the Earth. And to this end, we've created software to do azimuthal travel time analysis, amplitude analysis, and then also modeling. And the modeling, I think, is really key to understand the relationship, let's say, between fractures, the anisotropy, and then the travel times and the amplitudes. So it allows you to do forward modeling and try and understand the relationship between the rock physics and what we're actually observing. It's also possible, using a combination of strata and ProAZ, to do azimuthally sectored simultaneous inversions, and then to analyze all the information together. I'll talk briefly about that. And then we've provided some different graphical tools to view the azimuthal data, and we've extended many of the processes to include azimuths. So you could, for example, do radon on azimuth sectors, or you could do azimuth stacks and then analyze that, or generate different azimuthal supergathers. And we call these common offset, common azimuth gathers, and we'll talk briefly about that. So the basic outline I'll follow today is I'll first talk a little bit about the relationship between fractures and anisotropy, how fractures give rise to anisotropy, and then look at how we might observe this azimuthal anisotropy within our data. And our focus will be on both the travel times and the amplitudes. I'll talk a bit about modeling, and then new features, and Brian was mentioning the symmetry axis ambiguity, looking at far offset information to try and address that, and also uncertainty. How do we handle uncertainty? And then I'll summarize. So I always like to start with this slide, and actually I think it's attributed to Dave, who's sitting in the audience today, and it's really nicely summarizes how fractures give rise to anisotropy. Imagine we're looking at the Earth in plan view, and we have a series of vertical fractures that are a little bit more compliant than the surrounding materials. And if we send a wave perpendicular to the fractures, just do the time average equation, it's going to travel a little bit slower than if we send a wave parallel to the fractures. And just due to Fermat's principle, we'll find some path which avoids the fractures. And this is the very definition of anisotropy. The velocity varies depending on the orientation. And we're going to try and take advantage of this in order to try and detect fractures. So we might, our goal or our abstract ideal is that we're going to try and estimate vertical fractures such as were appearing in this limestone. And this gives rise to what's called horizontal transverse isotropy, or HTI. type of fractures we can deal with and the type of anisotropy is actually much more general than that, but I don't really have time to get into that today. But all of the equations we'll look at generalize to more complex types of anisotropy. Now, closely related to fracture-induced anisotropy is stress-induced anisotropy. And we can either start with an inclusion model or a contact model. And in the case of an inclusion model, what you would assume is that you have a series of small little cracks and they're randomly oriented with different sizes and orientations. And under an ambient stress conditions, when you measure the velocity, it appears isotropic. When you get differential stresses, what will happen is the surface area will change and you'll preferentially close some of the fractures, and you'll also observe anisotropy. So the two of these mechanisms are closely related. Now, I'll start off by looking at a very simple model. In this model we generated within ProAZ. We have an isotropic layer over an anisotropic layer over an isotropic layer, and both the P wave and S wave velocities exhibit a fast velocity and a slow velocity. And if we were to just do a very simple experiment where we have two lines, one being parallel to the fractures, one being perpendicular to the fractures. When we measure the travel times, what we'll observe is that we get slightly different move out when we move through the fractured layer. At the top of the fractured zone, they both exhibit the same move out. At the base, when you're going perpendicular to the fractures, just because it's a little bit slower, you're going to have a little bit more move out. And when we do our NMO correction, we look at some sort of average velocity, and then we correct it, the fast direction will be overcorrected, and the slow direction will be undercorrected. Now, we can shoot a series of lines at different azimuths, or we can simulate that by looking at a rectangular patch and create a geometry like this. And when we do this, what we'll end up with is data in a series of different azimuths. So we have an azimuth at 0 degrees, 22 degrees, 90 degrees, etc. And within each one of these common azimuth panels, we'll be going from the near offsets to the far offsets, and you'll see residual move out within here. And some will be overcorrected and some will be undercorrected. Now, when we look at travel times, it's often better to change the sort order. And when we do this, we have constant offsets, and then the azimuth varies. And this is what we call a constant offset common azimuth gather. And when we do this, what you'll see is that at the base of the fractured layer, you're going to have azimuthal variations which appear sinusoidal and grow as you get out to larger and larger offsets. And the fast direction, once again, is overcorrected, so that would be the peak, and then the base of the trough here would be the slow direction, and again this would be your slow orientation. And the degree of anisotropy is going to be the difference between the peak and the trough, and that's really an effective property all the way down to from surface down to the zone of interest. So it's an average type property. So we can this sinusoidal variation observed in the residual azimuthal travel times, we can model using an elliptical velocity function described by the fast RMS velocity, the slow RMS velocity, and then an orientation. In this case, we're showing the slow velocity azimuth. And mathematically, we can modify the NMO equation, and this is due to Svanken, and what we do is we allow the NMO velocity to vary as a function of azimuth, parameterized in the terms that you see here. So in practice, what we're actually doing when we do our azimuthal travel time analysis is we're going to go ahead and calculate the residual travel times at the zone of interest. We do this by just calculating the time variant trim statics and recording the values. And we can plot these as a function of offset and azimuth, and you'll get this sort of saddle-like feature here. And We'll then do a modeling exercise where we supply the original velocities or some background velocities. We remove those velocities and then calculate a fast stacking velocity, a slow stacking velocity, and then the azimuth of this. And this whole inversion is nonlinear, and we solve it in an iterative fashion. This slide here shows our interactive azimuthal velocity analysis and captures some of the details that we described in the preceding slide. First, this would be our common offset, common azimuth gather. And we're going to analyze this event, which is at the base of the Haynesville. This is from a data set from the US. And shown in the background is the time variant statics that were calculated from the trim statics. So the reds would be, I think, positive. No, actually, let's see, the reds are positive, blues are negative. And then we're going to plot the different residual travel times as little squares in this display. So we're showing the travel time as a function of azimuth, and then the color here represents the particular offset. And our far offsets here are going to be showing up in purples or blues. And so you can see when you look at the far offset data that there appears to be a sort of a sinusoidal variation to this. We can fit this data and we get an estimate of the fast velocity, the slow velocity, and the azimuth, and then we can predict what this is at different offsets, so the near offset, a mid offset, and then a far offset. So we're doing this curve fitting exercise and essentially to try and calculate these three velocity pieces of information. And we can then display these as separate attributes. And here, rather than showing them as the fast and slow velocities, I'm showing you the average RMS velocity and then the fractional difference. And the fractional difference just highlights the changes between the fast and the slow. You can display in a variety of different parameterizations, but you can see in this area here we have some large fractional differences. But remember, this is an effective property including all the effects from surface down to the zone of interest. So having calculated these velocities, we can then go in and do a residual azimuthal NMO correction. So this would be the input data after the application, so you can see in this particular area that things are flattened out quite nicely. And then for reference, we're showing the time variant trim statics at the base here. And our goal would be to try and get this to look as good as the time variant trim, but this has 3 degrees of freedom, this has many degrees of freedom, so we're never going to quite achieve this. But we've done a very good job in terms of flattening the gathers. When we go into the azimuthal AVO, we need to bring in flat gathers. So we can either bring in the residual azimuthal NMO gathers or the time variant trim, or maybe some combination where we do the residual azimuthal NMO and then run it with a very narrow trim window to avoid any sort of cycle skipping. So as I mentioned before, the RMS or stacking velocities, they are an effective property. We have to do, and they include the effects of anisotropy in the near surface. So they include the effects from the surface down to the zone of interest. So we need to do some sort of layer stripping to remove this overburden, and we do that by doing a generalized Dix inversion. So on the left I show the average velocity that was calculated. So we're doing a residual NMO correction on top of doing the azimuthal correction. And then over here we're also showing the fractional difference. And the neat thing about the fractional difference is when you work through the math for HTI media, the fractional difference corresponds to Thomson's delta parameter. So you actually have a physical meaning to the type of anisotropy that we're looking at here. And in this particular case, we're getting some sort of anomaly down at the Bossier level, which is known to be anisotropic in this area. And then we'll move into the visualization software and we'll show the fractional difference in the orientation. This is a data set we worked a number of years ago where there's a nice strike slip fault and then there's a little splay off to the left, and you can see how the presence of this fault here, the strike slip fault, alters the orientation and the magnitude of the anisotropy. So I want to move now on to azimuthal amplitude analysis. And again, remembering our very simple model, for isotropic layers, what we're trying to do is by looking at how the reflectivity varies as a function of incident angle, we're trying to infer our elastic properties within a particular layer. So not only understand the P impedance reflectivity, but by looking at how the amplitude changes as a function of offset, also say something about the S impedance reflectivity. And one simple way of parameterizing this is to use the two-term Wiggins expression, where we say that the reflectivity is equal to the zero offset P impedance reflectivity, or intercept. And then we have an additional angle-dependent term here, and the dependence is based on this isotropic gradient. When we move into an azimuthal world, the velocity is going to vary as a function of azimuth. And so our gradient term here is also going to vary as a function of azimuth. And I'll return to this equation in a couple of minutes, but what I'll do now is let's look at this model that we were looking at earlier on. And we're going to look at the interface going from the isotropic to the anisotropic media. And we'll do our analysis right at the top of the zone of interest. When we look at amplitudes here, it's quite subtle to actually see this unless you actually plot it. Again, we're looking at reflectivity, or amplitude, as a function of azimuth, and we have it color-coded, so we're looking at data from different incident angles. So we're taking our data in offset, transforming it to angle, and then we can plot the amplitude versus azimuth for a particular incident angle. And when you get out to the larger angles, it becomes really obvious. You even get a polarity reversal here, and you can see how it changes over here. And I'll return to this display in a couple of minutes. So this is a data set which we've created a common azimuth, common common azimuth, common offset gather. And so we've just regularized it and calculated at a particular well location. So within each one of these gray panels, alternating gray-yellow panels, we can look at how the amplitude is changing as a function of offset. And this is the Nordegg down here, this green marker. And what you see is that the amplitude versus offset, which is parallel to the maximum stress, which is about 45, is quite distinctly different than what it is at 145 degrees. Here we're almost getting a class 2 anomaly. Here it's the amplitude is remaining quite consistent all the way across. And so by looking at these types of gathers, we can take a look for the amplitude versus offset. We have a number of different ways of trying to quantify this. We can go in and do an interactive azimuthal analysis, and there's a list of different options. I'm going to focus early on in the talk just talking about the near offset Ruger equation and the azimuthal Fourier coefficients. So just returning back to this expression we saw previously, this is the near offset Ruger equation. And as I said before, if you just have the first two terms, this is our isotropic case, it would be the Wiggins approximation. But we have two additional terms which are perturbing the gradient as a function of azimuth. That is the anisotropic gradient and then the isotropy plane azimuth. And this would be the same as your fracture strike in HTI media. This anisotropic gradient, if you use Hudson theory to model it, it turns out to be proportional to the crack density. And so sometimes people will relate this back to crack density, though the interpretation of this is more complex when you start looking at linear slip theory. So what we can do in the next series of slides is I'm going to use the Ruger equation to try and fit my data. And so what we see here is this is our seismic data. We're going to look at how the amplitude varies as a function of azimuth at this red marker here. We'll plot the amplitude as squares as a function of azimuth and also the incident angle, which is shown in color. And then we'll fit it using this near offset Ruger equation, and the model prediction is shown with these curves off here to the right. And we can see an azimuthal variation. It's actually a little bit more obvious when we look at the amplitude versus angle here. The near angles in this particular case are quite cruddy, but when we get out to further angles, maybe beyond about 12 degrees, we see that well, first off, we're fitting the basic amplitude versus angle trend here. We show that in red. And then the actual data points are shown in color as a function of azimuth. And we see that we have a systematic shift around our regional trend here, going from green all the way into the reds and into the pinks. So we're going from about 24 degrees up to about minus 72 degrees. So we have this amplitude versus azimuth around our regional AVO trend here. Another way of looking at this data is in plan view, where we look at the reflectivity displayed in color, displayed as a function on the y-axis, it's incident angle, horizontal axis, it's azimuth, and the data is shown as little black squares. So you can see the limitations of the data. In the east-west direction at 90 degrees, we only have data out to about 22 degrees, whereas all the other directions we have data out to about 30 degrees, which is what we'd ideally like to do our type of analysis. In the background, we're showing the modeled data, and in the foreground with the dots, it's color-coded again by amplitude. So they sort of blend into each other. We have a good fit in terms of our prediction. Another way of looking at this is in the polar view. And I kind of like, well, both of them have their strengths. It's a little bit harder to see the data problems with this particular display, but it's easier. You can see that we're actually modeling it quite nicely when we look at the far angles, which is the real key thing when we do this type of analysis. Now, rather than looking at both the amplitude versus offset and azimuth, we can restrict ourselves to just looking at the amplitude versus azimuth. So, for example, if I was to look at the amplitude versus azimuth at 35 degrees, I would see some sort of sinusoidal behavior. And I can decompose this sinusoid into a series of constituent parts. There's going to be a DC component, a sinusoid of periodicity 2, and then a sinusoid of periodicity 4. And when I add all of these together, I end up with my original signal again. And what's very interesting is that each one, the magnitude and the phase of each one of these sinusoids has physical meaning. So, for example, I'm restricting myself to HTI media today, so I'll show you the HTI expressions, but we can do this also with orthorhombic or, let's say, vertical fractures in the VTI background media. We're going to have our P-wave reflectivity. It's going to be the sum of these sinusoids, where R is the magnitude and phi sim is the phase. So the first thing to take from this is that the phase of these sinusoids is governed by the symmetry axis or the fracture normal. And then the magnitudes, the 0th order or the background or average, that's just governed by the 3-term AVO expression. The 4th term, it turns out to be related to the change in eta. And eta is the analypticity. So if a media is elliptical, you can describe it by its fast and its slow direction. If it's analyptical, you need an extra parameter to describe the deviation from the analypticity. So this is describing how elliptical the media is. And there's a certain nice symmetry to that, because when we do our NMO expressions, it's analypticity which controls the long offset NMO. And then the second Fourier coefficient here, it's largely at the near offsets controlled by the anisotropic gradient, which we saw previously in the Ruger equation. So this is just some synthetic data. One is generated with an elliptical anisotropy. The right hand is generated with an analyptic media. And the major difference is just this 4th Fourier coefficient. For the analyptic media, you get a non-zero fourth order Fourier coefficient. And it's thought that stress-induced anisotropy gives rise to elliptical media. And this is just the definition of eta here. When epsilon equals delta, the media will be elliptical. So, and I know some of our clients are using this fourth order to try and predict fractures, and they've had some success with that. Now, the one that most people will focus on is the sinusoidal second order periodicity. And here again, we're looking at the amplitude versus azimuth. The data is color coded. We're looking at data from 20 to 30 degrees here, the reds being smaller angles, the purples being larger angles. And when we plot the average periodicity, we get a curve that looks like this over 180 degrees. And it's going to be described by the peak to trough magnitude and also the phase of this sinusoid. When I look at the peak to trough magnitude, I'm getting a measurement of this magnitude here, and I know the average angle of incidence, so I can manipulate the expression and get an estimate of the anisotropic gradient, and this will appear to be very similar to what you get out of the Ruger expressions. The other thing you can look at is the phase of the trough. So for positive B ani, this turns out to be your isotropy plane azimuth, which is the same as your fracture strike in the case of positive B ani. And so just looking at this gives you quite a bit of information about the type of anisotropy you have within your data. So if we were to actually analyze our data using the interactive program, you'd bring it up, you could look at Fourier coefficients at different angles of incidence, and then you could restrict yourself, let's say, just to the maximum angle, and then turn on and off the individual Fourier coefficients, and then trying to understand what you're actually observing within your seismic data. Now, in the preceding slide, we were essentially getting two pieces of information, the magnitude and the phase of the sinusoid. And we were doing it for one particular event at one particular CDP. So what we can do is when we create the volume attributes is we'll calculate this for every CDP, and we'll do it for every time sample, and we'll output the magnitude on this for this volume and the phase for this volume here. In this particular case, we're doing it for the second Fourier coefficient, but we could also do it for the fourth coefficient, or we could do it for the DC. And so what we see here is we get an estimate of the anisotropic gradient, and then also our symmetry axis. And then knowing these two pieces of information, the magnitude and the azimuth, we can then create this 3D visualization display where we have both magnitude and orientation information, and then try and relate this back to our well control and look for correlations. And relate it back to either fractures or to the stress field. Now, the major thing I wanted to talk about, or the last component, is the azimuthal modeling. And the basic idea of the modeling is that we'd like to be able to model what the P-wave azimuthal amplitude and travel response is due to the introduction of fractures. So when we're trying to interpret, it's a two-step process. We measure the amount of azimuthal anisotropy, and then we're going to try and do modeling to try and understand how much we should actually expect within the data. And we could test different things like modeling the AVA response to the fractures. We can see the sensitivity to this, to different noise levels in our data set. We can put different fluids in and see the influence of that, see what happens if the fractures aren't vertical, how that modifies the response, and what happens if we have, let's say, a shale with a VTI background, what happens if we put fractures in that compared to, let's say, a sandstone. And so you can do sensitivity style analysis for that. Most of the things I'm talking about today is focused on fractures. Olivia's busy in the background, and she's going to release some different tools to do stress-induced modeling, and so we're really interested also in pursuing that. She has some working software on that as well, and we'll release that in the spring. So with the fracture-induced anisotropy, our basic model is based on linear slip theory following Schoenberg, and the basic model is we're saying that the total compliance of the rock is equal to the background compliance of the rock plus an extra compliance due to the fractures. Compliance is just how easy it is to squish, whereas it's the opposite of stiffness, or the inverse of stiffness, which is how hard it is to squish. And we use a couple of Hooke's law-like relationships to describe the fracture parameters. One is if we apply a normal stress across the fracture, there's going to be a little bit of displacement. And the relationship linking the displacement discontinuity to the normal stress, the proportionality constant is the normal fracture compliance. And the other one in the tangential direction is called the tangential fracture compliance. And these two parameters are enough to describe the fracture. If you have a liquid in there, it's going to be stiffer and it's going to change the normal fracture compliance, but it shouldn't impact the tangential fracture compliance. One way of parameterizing this is in terms of the BN to BT ratio. Verdun and Vestavel, they published values for this going from between 0 and 2, and with a median value of about 0.5, so we know what the limits are, and we can use that as one of our parameters to control the modeling. Rather than working with these compliances which have units of like 10 to the minus 14 gigapascals, we can rewrite them as fracture weakness parameters, and therefore they're fractional, and they have a value between 0 and 1. 0, there's no influence. 1, it's the upper value. So when we do our modeling, we'll specify our background model, and we might put in, it'd be very similar to doing AVO modeling. You specify the P velocity, the S velocity, and the density. Then we talk about the fracture, and we can specify the tangential fracture weakness and the normal fracture weakness. And then in the background, the program calculates the stiffness matrices. You don't even have to look at it. And then from that, it generates a synthetic gather. And then we can look at how the amplitude or travel time varies as a function of azimuth. And we can go into the interactive program and then view how the amplitude varies as a function of azimuth. And we can also then compare our real data versus the synthetic data and see how close they actually match. So this display here, we're looking at the amplitude versus azimuth. It's hard to see, but some of these are triangles and the others are squares. But when you get close, you can actually see the difference between the two of these. And so one represents the real data, the other the synthetic data. It's easier to look at the AVO data, and when you look at the AVO data, what you see is you get two different trends. And this might be due to the presence of background VTI anisotropy. So we follow the method of Lin and Thompson. I know when he was here at the CSCG, he was talking a couple of weeks ago at the beginning of November, he was talking about this approach. And the basic idea is you compare the different AVO trends and then put in VTI anisotropy to try and match up the two different data sets or the two different AVO trends. And then you try and infer what the background VTI is by changing these trends. And this just shows the introduction of background VTI anisotropy. And then we can compare and match up our synthetic data much closer to the real data. And so in this case, it's possible to create synthetics with very believable parameters that actually predict the azimuthal amplitude variations that we're observing within the real data. So I wanted to now move on and just talk about some of the new features we've put into HRS10. And we've already talked about the interactive azimuthal velocity analysis. What I wanted to focus on now is just to say that we've modified the software so it's possible to do an independent azimuthal inversion. So the basic idea would be you would create common angle, common azimuth sector data, and then you'd work on one particular sector and do a simultaneous inversion, for example, for P impedance and the VPVS ratio. And then you can group all the data, let's say the VPVS ratio, as a function of azimuth. And then you can analyze this by going into that interactive program we were looking at earlier, the azimuthal amplitude, or the volume analysis. And we could calculate the second Fourier coefficient on this, which is very similar to an eccentricity type of analysis. And this just shows the eccentricity that was calculated based on the VPVS ratio as a function of azimuth. And this gives an anomaly very similar to what we saw from the azimuthal Ruger, or from the Ruger equation. This is similar to the frac vista flow that Erika Unger published a number of years ago when she was at CG.
Panels on the left are separate inversion?
Yeah, so each panel would be at a particular inline, and then within each panel we're observing the data as a function of azimuth. And then what we're doing is we're just looking at how the amplitude or the VPVS ratio varies as a function of azimuth, and then quantifying that and looking and calculating the fractional difference within that area. So the next thing I wanted to talk about was the symmetry axis ambiguity. So the first thing I'll talk about is what gives rise to that symmetry axis ambiguity. Remember that our gradient now varies as a function of azimuth. If the material was isotropic, the gradient would be a circle. It would be azimuthally invariant. If the material is anisotropic, you get what appears to be like an ellipse. Essentially, the circle gets perturbed, and in the orientation, if you have a positive B ani, along the major axis, you're going to have a perturbation, and then along the minor axis, which is the isotropy plane, there will be no perturbation. The gradient will be the same. So you'll have essentially you have an ellipse described by three variables: the isotropic gradient, the sum of these two, and then the orientation of the ellipse. And problems become, though, when you get the anisotropic gradient can be both positive and negative. We've already looked at the case where it's positive. We move from this red circle to the blue ellipse. You essentially have a positive perturbation. And the symmetry axis then corresponds to the major axis of the ellipse. The problem is if the anisotropic gradient is negative, and then we're going from this black circle to the blue ellipse, and in that particular case the symmetry axis is the minor axis. And so your orientation can change depending upon the sign of B ani. When we estimate B ani, all we're getting is a magnitude information. We don't know its sign. And this is in particular with the near offset approximation. And so what that means is that when we look at this anisotropic gradient here and we look at the associated azimuth, when we output this anisotropic gradient, we're always assuming it's positive. But in reality, some of these values are negative. And what this means is that you get, when we're estimating as a positive, it's actually negative, you're getting a flip in the azimuth orientation. So we get this alternating sort of purple-yellow alternation where we're going, let's say, from about 20 degrees down to minus 70 degrees. So one way around it is we say we're not going to restrict the solution so that it's a positive value. We're going to say, well, we have a rough idea of what the azimuth is, and this rough idea could come from a variety of different places. It could come from the maximum horizontal stress orientation from the worldwide stress map, or maybe local well control, or maybe cross-dipole logs. And then from this information, what we can do is we can constrain the orientation and say that we are going to choose the orientation which is closest to this dominant direction. And when we do that, we choose the orientation which is closest to the dominant orientation. We're going to allow the anisotropic gradient to be both positive and negative values. And this is the result in the middle, which shows this new azimuth orientation in contrast to the other one. And this is going to be much more consistent. This is always consistent, let's say, within the 70-degree range with this particular data set. So we can do that with the near offset type of analysis. And when we look at two alternating layers where the anisotropic gradients change sign, in both cases we're going to get a consistent orientation in terms of the fracture strike. Another way of analyzing this type of azimuthal data is to go in and look at it in a rows diagram. You can go in and then interactively pick a particular location, and then you get a distribution of azimuths at that particular location. Now, the other way we can go after the symmetry axis is by doing a far offset inversion. And I'm not going to go into the details of this, but I'll just say that we can do a 7-parameter AVO AZ inversion, or also small parts of subsets of it, like the approach that Benjamin and I published back in 2011. That's a 3-parameter inversion, which is a subset of this particular inversion. And I'm writing this on the left-hand side. The data has been transformed to Fourier coefficients. On the right-hand side, they're just generic parameters which can be transformed to, let's say, Thompson parameters to fracture weaknesses. And the thing I'll do a talk later on at GeoConvention more on this. I don't want to get into the mathematical details. I'll just say that this appears to be a linear set of equations, but we do have the azimuth sitting within here, so it's actually nonlinear. So the way that we go ahead and solve this, or a brute force way of doing it, which is easy to understand, is that you can essentially go ahead and do a least squares inversion where you iterate through different values of the symmetry axis. And then for each value, you do the least squares inversion, you calculate the misfit, and then you choose the minimum solution. And where you get the minimum, this will correspond to where the symmetry axis is. But what actually happens is that instead of getting a global solution, there's again 2 solutions, and so we have to put in a rock physics constraint. And the basic idea is we're going to do something very similar to what Benjamin and I did a number of years ago, and we'll say that we're going to choose the solution in which the vertical fracture weakness is close to the horizontal fracture weakness, and that's going to be the more physical of the 2 solutions. And when you plot the data in the different solution spaces, usually one will be sitting way off in the left-hand corner, the other one will be much tighter scan. It's much more tighter in terms of where the solution are. Essentially what we're doing is we're using rock physics to reduce our solution space. And then after having solved for the generic transformation, we can then transform the data to different parameterization. So for instance, here we're transforming it to fracture weaknesses. So we have the vertical, the horizontal, and the normal fracture weakness. Here's a display from the interactive analysis where we're looking at one particular reflector, and we're plotting the amplitude versus azimuth, and we're using quite large angles here. And then from that, we can estimate the intercept, the isotropic gradient, the curvature term, and then these 3 fracture weakness parameters. And I've plotted the estimate versus the actual down here, and they're all within about 10%. We can do this also as a volume style. I have a synthetic gather to the left, and then based on the synthetic gather, I can estimate the normal, the vertical, and then the horizontal fracture weaknesses. When you go into the fracture, you're getting a positive reflector, and then when you leave the fracture, we're getting a negative reflector. And by that, and by looking at the signs, you can see that we're getting the right phase associated with the symmetry axis. Now, I have some different thoughts about using this far offset AVO inversion. The 3-parameter AVO inversion is a subset of the 7-parameter problem. And so we know that the 3-parameter has stability issues, so I think it's going to be only in exceptional circumstances where we can do this real long offset. And so this might be more of a modeling curiosity that you can go ahead and do your far offset Ruger equation or look at other types of parameters. I think it's probably better to look at smaller portions of the problems if we're going to try and get a more stable answer out of this. So this leads on to the question of data requirements. In order to get reliable AVO-AZ attributes, we need to have a good distribution of incident angles. If we're just doing trying to estimate the anisotropic gradient, if you look at data from, let's say, 20 to 30 degrees, or in the 30-degree range, I think that's really the key range of angles. If you want to go to higher order inversions, we're going to need in excess of 45 degrees, which places greater requirements on the processing and the acquisition. We need a good distribution of azimuths. If we're just, again, looking at the sinusoid of periodicity 2, we need at least 4 distinct azimuths. And so maybe 0, 45, 90, 135. If we have COV data, the COV data is naturally sampled at tighter angles at the far offsets than at the near angles. And those are where your key data is. It's at the far offset. So the COV is actually better than moving to this azimuthally sectored style of data. If we're going to go for the 4th Fourier coefficient, we need at least 22.5 degrees sampling. And we also need a good signal to noise ratio. So we've tried to create some different QCs now to allow you to see what your data actually contains. So for example, you can calculate the range of incident angles, so it's the maximum minus the minimum. And this is this display to the right here. And what you see is in the shallow section, just because we don't have near offsets, we have a relatively narrow incident angle range, and we're going to run into some stability issues because of that. Also in this data set, there's a velocity aversion associated with the shale, and again we have a more limited range of angles, so there's going to be some other problems. We can display the live fold. That tells you something about the signal to noise, and also the correlation coefficient. It tells you something about the data misfit and how good the data misfit is. One thing we've done with this last version is we've put the ability to mask uncertain output. So based on uncertainty estimates, we can exclude, or we will not output data that's relatively uncertain. So in this particular case, anything above this horizon here, it's a narrow angle range, and it caused problems with the estimate of the anisotropic gradient, and it's sort of blowing up here. So what the program now does is there's an uncertainty threshold that's defaulted, and it won't output in this particular situation, like at the edges of the survey. The other thing we did was we put in the ability to estimate the uncertainty based on a paper Dave Gray and I did back in 2006. And the method will estimate the standard deviation of each of the attributes, assuming Gaussian statistics. And the uncertainty is really based on 2 factors. One is the signal to noise, and we estimate the signal to noise based on the misfit. We calculate the misfit and then calculate the standard deviation from that and then compare that to the model. And then the other one is looking at the offset and azimuth distribution of the data. So there we calculate the linear operator, and you work with the linear operator in calculating what the uncertainty is. And by doing this, we can sort of create this whisker display where we plot the standard deviation on top of the glyph. So this would be a glyph. The length of the glyph is proportional to the anisotropic gradient, and the orientation is the azimuth. Now we'll put the standard deviation of the anisotropic gradient plus or minus here, so this would be plus or minus 1 standard deviation, and then the azimuth is plus or minus 1 standard deviation. So it's going to be hard to see from the back of the room, but there's little whiskers around each one of these glyphs. They show up as orange values, and they give you an idea of the degree of uncertainty. And when you get up into this corner, you have, it almost appears to be like crosses, so there's a lot of uncertainty associated with them. But when you have higher values, there's a lot less uncertainty. So at least it gives you one way of trying to understand the degree of uncertainty associated with the different values that are coming out here. So to conclude, what I've tried to show today is how we can use both azimuthal travel times and amplitudes in order to capture the degree of anisotropy within the data set, and then show you how you could do forward modeling to try and establish the relationship between fracture-induced anisotropy and these azimuthal variations that you're actually observing, all with the goal of trying to look at the placement of your wells and also the pad placement. So thank you for your attention, and so if you have any questions, I'd be more than happy to answer your questions.